Okay, thank you for attending. This is an extra lecture on Chapter 7. So we're going to start where we left off on Thursday, which is the first law of thermodynamics. First law of thermodynamics just says that energy is conserved. And so when we see this particular equation for the first law, which is shown here, if the system loses energy or gains energy, that energy comes from the surroundings or goes to the surroundings in the form of heat, Q, and work, W. And these are the things we can measure, heat and work. Although we do calculations for work, we can also do calculations for heat instead of having to do calorimetry for the measurement. And so we can determine how much heat and work is involved in an internal energy change. And that turns out to be very useful. And so we'll talk about this. I was talking about state function as well here, which is important too. Basically, if we have an isolated system, it's unable to exchange either heat or work, and therefore delta U, the total energy change in an isolated system, is zero. And so here's our system here in green, and so we can lose heat, that's losing energy in the form of heat, and we can lose energy in the form of work. And so in this case, what we say is that the system lost heat and does work. When we say does work, then the system is doing the work. Whereas over here, in this case, the system gains energy as it absorbs heat. So in this case, it's absorbing heat. And a strange thing happens here. If the surroundings does the work, then the system benefits from that. And so what we say over in this scenario is that the surroundings does work on the system, therefore the system gains energy from the work that's done on it by the surroundings. When we have state functions or functions of state here, it's any property that has a unique value. For example, temperature. Temperature delta T only depends on T final and T initial. So if we look at delta T, it depends on the final state and the initial state. The same thing with delta P. Delta P only depends on the final state and the initial state. And so temperature and pressure are what we call functions of state or state functions. The one that we have to worry about is heat and work. Q and W are not state functions. And so what that means is that the amount of heat and the amount of work don't depend on the initial and the final state. They depend on how it was let's see, pause this. How it was done, the transition between going from the initial to the final state, and we call that the path. And so Q and W are not state functions. Instead, they are path-dependent functions. Functions, FNC. And so let me give you an example of that here. Let's see. U is a function of state here. Oops. And so what that means is that delta U has a unique value between two states. This is easily measured. Actually, U we already talked about. U is not easily measured because of the potential energy. The absolute potential energy. And so the absolute internal energy, What happened to the lights? The absolute internal energy is not measured, but what we do is we measure delta U. And so what that means is we don't determine U2 and U1 instead, or U1 and U2. Instead, what we do is we determine Q and W. Q plus W, these can be measured or determined. And so this is also going to equal Q plus W over here. Now, the delta U doesn't change. And so delta U does not change. And so it's like a fixed property of the system here, the change in internal energy. But the Q and W do. So, for example, if Q is high and W is small, that's one way of doing it, or we could do a lot of work and not much heat. And so if we go back to the slide that I'd shown earlier, here, the amount of heat depends on how you do the drop. The gravitational potential energy here in this earlier slide doesn't change. So delta U is the same regardless here, because delta U only depends on the initial, which is U initial, and the final, which is U final here. So delta U is fixed, let's say, for this particular slide. And so this is the same delta U over here. We're starting off with the same initial and the same final. But the amount of heat that's generated and the amount of work that we do varies. So for example, this one could be converted into all heat here as you slide down. If you're making noise, then you're creating some work, by moving the air molecules there. And so it depends on how much noise, squeaking noise or whatever you do, that could increase the amount of work or decrease if there's less noise, go down quietly. And so the amount of heat is not always the same. Each time you go down the slide, you aren't generating the exact same amount of heat, and you aren't generating the exact same amount of work. In other words, it depends on how you go down, and that's called the path. And that's the path-dependent function. So over here, we're minimizing the amount of heat and maximizing the amount of work by having the rope going through a pulley and attached to a mass. And so in this case, the work has been maximized. So the amount of heat is minimal, but the amount of work is large. And so the delta U is fixed. However, the amount of heat could be large, like in the left scenario here, and the amount of work small. Or it could be like in the right-hand scenario here, where the amount of work is large, but the amount of heat is small. So what we say is that Q and W are not state functions. So I'm going to just move this back. Over here. We'll insert that. A new slide. Here. So delta U6 is depending on the gravitational potential energy, which is the height, and the height doesn't change. And so this is why I say delta U is fixed here. But Q and W are not fixed. And so in path-dependent functions, the amounts depend on the path. It's path-dependent. Whereas in state functions, this is state function, it does not depend on the path. And so the amount of gravitational potential energy depends on how high this person is. The same thing. This is the same. We have to be aware of that. And so this is what this slide is saying. Changes in heat and work are not state functions, basically. And so this is an example of that, which I'm going to skip here. We'll look at other examples later. It just depends on how it was done. This is two-stage versus one-stage expansion. You don't have to worry about this. We'll look at other examples of this. So if we do no work, then all the internal energy change here is converted into heat. There's no work here. However, if some work is done, then we don't get as much heat. This is work done by the system here. And over here, we have not work done by the system. This is work done by the surroundings. The work done by the surroundings, if the surroundings does the work, then it adds energy to the system, and the energy is here shown as an extra Q amount. And so it depends on how much work. No work, work done by the system, and this could be bigger or smaller depending on how much work is done. You could do more or less work, and then work done by the surroundings. So this is the same thing. You could think of a battery. If you have a battery, does it always give off the same amount of heat and the same amount of work? No, it depends on what you put the battery in. If you put it into like a little electric toy, you might get a lot more work than if you put it into a flashlight or a heater, electric heater. And so we'll look at these things. So the point of this being that internal energy change, delta U, is fixed. However, the amount of heat and the amount of work is not fixed. Here. And so let's take a look at 7.6 applications of the first law here. And so recall, we don't calculate these. These are called absolute internal energies are not determined accurately. Absolute internal energy is typically not determined. People try to determine these, but the errors associated with its calculations are too big for us to really use. However, this is determined. Okay, in a system at constant volume, like for example in a bomb calorimeter, you can't do any work. And so in a bomb calorimeter, the work term is 0. Here. It's just stuck in this bomb. And so all the internal energy is converted into heat. We call that QV. And so this is very important. Bomb calorimetry measures QV. That's what we get from it. And QV is the same as delta U. And so we can determine delta U using bomb calorimetry. But, this is a big but here, we don't live and work inside a bomb. We live in a constant pressure world. And so QV isn't as useful as QP. QP is going to be much more useful for us. And so, but there's a problem, in a bomb, you can't do any work. Okay, but in a constant pressure world, normally work can be done. And so let's add a couple of slides here. So in this section, we're going to make QP. QP is not a state function. And so the amount of heat is hard to predict because it depends on how much work you do. So QP is not a state function. Therefore, it is, okay, QP is not a state function, as I mentioned. Therefore, the amount of heat depends on the amount of work. And so here we have delta U is equal to Q plus W. And then what we are going to do is we're going to restrict ourselves to the constant pressure universe. And this is going to be delta U is equal to QP. Oops. QP, which means constant pressure, plus the work. And then we see that QP is equal to delta U minus the work. And so it depends on how much work is done. Now we have lots of different types of work, so this is going to equal delta U minus, okay, what types of work is there? Well, there's pressure volume work. The pressure volume work is like blowing up the balloon, that we saw earlier. Plus there's electrical work, plus there's mechanical work, like lifting a mass, etc. Plus, etc. Dot, dot, dot. So lots of different types of work. And so it depends on what you're doing with this energy. The internal energy is fixed. And so this is the chemical potential energy here. And so if we take all that potential energy and then we subtract all the work that we do or that's done on it, or however we do this, then that's how much heat we're going to get released. And what would be very useful is if we could always have a consistent amount of heat that's released in there. And so what we're going to do is we're going to make QP into a state function. It would be useful to make QP into a state function and call that state function. This is a new state function, delta H. Delta H. Here. So how would we go about doing that? And so how we would go about doing that is this. So I have, so far I have QP is equal to delta U, which is a state function, okay, minus the work. And so this is PV work plus whatever work, we might not have any PV work, we might not have any electric work, plus dot, 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 all the work. And so the first thing we do is we restrict it to only PV work. And so restrict to constant pressure and PV work only, pressure volume work only. Pressure volume work has to be done, otherwise we might have a pressure explosion or an implosion. And so if you're going to carry out a reaction at constant pressure, then the volumes have to be able to expand or contract naturally. Since the volumes have to expand and contract naturally, we call this the natural work of a chemical reaction. The natural work of a chemical reaction. So if we go back to this slide here, actually not this one, let's go back to this slide here. Is it this one? Nope, sorry, still wrong slide. This slide, yeah. If we go back to this slide here, there are two ways of doing this. We could do this at constant volume. Here. Constant volume would seal this container, so we'd have to make sure this lid is sealed or glued shut. Therefore, as the oxygen is being generated, it's just going to expand to fill this container, and the pressure is going to go up. If you want to do this under constant pressure, then this lid has to be able to move up and down to compensate for increases and decreases in volume. And in this case, we have an increase in volume, and this is to maintain constant pressure. And so this increase in volume we call the natural work of a chemical reaction, because as we generate gas, that gas has to expand, and therefore the gas expanding is going to do work. If we consume that gas, let's say go backwards, then the gas has to contract. And in that case, the surroundings has to do work, because the surroundings volume increases. And so the surroundings would be blowing up the balloon in that particular instance. Let's get back over here. Slide. And so the natural work of a chemical reaction means, we have three scenarios. One, the volume increases of the system. System does work. Two, the volume decreases in the system. If the volume decreases in the system, then the surroundings blow up the balloon. And so what we say is the surroundings does work on the system. In other words, the surroundings doesn't work, the system gains that energy. The last scenario is, let's say there's no gas formed and the volume of the system is fairly constant. Then no work is done under constant pressure. This would be like if we took 50 milliliters of hydrochloric acid and add 50 milliliters of sodium hydroxide solution, then there's no work done because there was no change in the volume. It's 50 plus 50 is 100 milliliters at the start, and then we have 100 milliliters at the end. And so this is a case where we could do it under constant pressure, and there's no expansion or no, in other words, there's no natural work of a chemical reaction happening in that particular scenario. And so no work is done. So what we're going to do is we're going to restrict it to constant pressure and PV work only. And so what that's going to look like is we're going to have QP is equal to delta U minus the work PB. And all these other works we're just going to call zero. Now, of course, we can do electrical work and whatnot, but here we need to restrict it. And so it's just PV work. PV work is called P delta V minus P delta B of the system. So this is just going to be delta U of the system, right, minus P delta B of the system. Here. And this is P external. So this is the only work that's done. Now, when we look at this, pressure, this is a state function. And volume, delta V, changes in volume, this is also a state function. The change in volume only depends on V final and V initial. And so these are all state functions here. And so what that does is it makes QP, which is not normally a state function, into a state function. So what we'll do is we'll define QP differently here in this case. Instead, what we're going to do is, now that this is a state function, we're going to call QP no longer QP, but we're going to call QP is a new state function. QP is going to be defined as delta H. So this is our heat. This is the heat of whatever. But now it's always the same. This is always the same amount of heat. It's always the same amount of heat because we always do the same amount of work, for that particular system. So going back to this previous example up here, if we're always generating the same amount of work, then we should always generate the same amount of heat, So, let's take too long to get back there. So let's do this here. Always the same for a given initial and final state. This is very good because now we can predict how much heat should be generated in this particular reaction. And this is going to equal delta U minus P delta B. Oops. P delta B. I'm not going to distribute the negative sign. So what are they doing here? They're showing that we already know QV. QV is delta U. Because if we do it where there's no work possible, then we know that delta U is the same as QV. It's slightly different because QV is the amount of heat, and the same thing goes with QP. It's the amount of heat for a given quantity, but delta U is an intensive property. QV is an extensive property. So delta U is usually normalized per gram or per mole or something like that. We'll talk more about that as we go on. Anyway, delta U is equal to Q plus W. And then we restrict the work. We only have one type of work, and that's pressure volume work here. And therefore, we end up with this. Their derivation is a little bit different than mine here. And they get the absolute enthalpy, absolute U, absolute PV. And so I don't really pay much attention to this derivation here. What we would do is we would look at something like this. So basically, I have this. Delta H is equal to delta U, minus W, where W is equal to P delta B work. All right, the way I think about this particular equation is like this. If you get a job and they tell you, oh, you're going to make $1,000 for your paycheck. And so this would be the gross income. And so they tell you you're going to get $1,000, but you end up getting less than $1,000. Depends. It depends because what happens is your pay is going to be taxed. And so you might end up with less than, let's say you end up with $900. And then you go, why didn't I get the full gross income? And the reason is because you had a tax. And in this case, you had a $100 tax. And that tax is the work. Let's say you had to do $100 worth of work. Then you aren't going to net that. I mean, $100 worth of PV work, I should say. And you end up with that. There are other scenarios. The other scenarios are, let's say this is equal to delta U minus W. Let's say the tax is zero tax. For example, there's zero tax they're talking about on tips right now for the presidential election. And so let's say there was zero tax. And so let's say you earn $1,000 in tips. Well, this is very nice because if you have $1,000 in tips and gross income, then you got your take-home pay will be $1,000 because there's zero tax. That is, there was no work done. We have cases like this, when we have a tax, let's say like this. This is what we're getting here. I should do it. Let's see. Maybe I'll do it like this: minus 900 minus. This is minus. This is how much we're going to net as the surroundings, let's say. So we're the surroundings anticipating this payoff. And so that's why I changed the signs here. But this is like the tax, the system volume expanded. So system delta V, in other words, is greater than 0. So the system does work. As you recall, work is minus P delta V. And if delta V is positive, then the work would be negative. A negative times a negative gives us positive, cutting it down here. In this case, if we have 0 tax, then this is at constant pressure. So delta V of the system at constant pressure is that. This is a scenario where delta V of the system is equal to 0 at constant pressure. So we didn't have to expand or contract the volume to maintain constant pressure here. And the final scenario is this. This is what everybody would prefer. Everybody would prefer that there was no tax and we just get additional income from the surroundings. So this would be like getting a refund or something where you get more back than you put in. And so this would be something like here. Oops, let's do this. Where this is a bonus. So let's say the net payout to the surroundings is $1,000. So you're expecting $1,000. You're the surroundings. But you end up getting $1,100. Well, why did you get more than the total? You got more than the total because some came from the surroundings. And so in this case, delta V of the system is less than 0, which means the system volume shrinks. So if the system volume shrinks, then what that means is that the surroundings does the work. And so this is minus P delta V. And so that's going to add a little bit of bonus. As this term is going to come out positive. Let's see, no. Delta V of the system, negative times negative is positive, yes. And then that's a positive and that's a minus, so we end up with less. Actually, we'll go through with some numbers so we can see this rather than visualizing this. This is at constant pressure. So those are some scenarios here. These are the 3 scenarios we'd see. We'll have a tax, 0 tax, and a bonus from the surroundings. The taxes to the surroundings. All right, so we'll take a look here at these. So what's going on here? We have CO and O2 and CO2. This is fixed volume. As you can see here, the volume can't change, so it's constant volume. So the heat, QV, is delta U in this particular case. And there's no work that can be done at constant volume. And so all the internal energy change is converted into QV. Here. It's constant volume. And so this is a scenario where there's no tax, but we can't think of it this way because when we apply the tax, it all has to be a constant pressure, not constant volume. So we have to look at what delta B is of the system at constant pressure. When we have a bomb like this, it doesn't have to be at constant pressure. In fact, when we look at this, we have 1, 2, 3, 4, 5, 6. Over here we have 4. So what's going to happen is the pressure is going to go down. But it can't it can't collapse the volume to maintain constant pressure because there are these tabs holding the lid in place, and so no work is done. However, if we do this under constant pressure conditions, now we can see is it a tax or bonus or zero. And so in this case, the system volume went down. The system volume goes down, that means the surroundings volume goes up. So the surroundings does work. If the surroundings does work, then the system benefits and we end up outputting more heat, more energy. And so this scenario here is this case where we have the net. We're going to net more energy. And so let's say up here, delta U is minus 1,000 kilojoules. And so let's say this is delta U, which is QB, which is minus 1,000 kilojoules to the surroundings. So the surroundings is going to get positive 1,000 kilojoules. But over here, what we see here is this work done by the surroundings here. And so the amount of heat that we're going to get is actually more. And so let's say the amount of work here is P delta B. The delta B here is negative. And so we end up with negative times negative is positive times negative is negative. So let's say this is 100 kilojoules. And then the amount of heat here is going to be plus the work, which is a bonus here of negative 100. So we're going to get negative 1,100. And so what that means is that the surroundings is going to get 1,100 kilojoules of heat rather than 1,000 kilojoules of heat due to the work of the expansion of the gas. So in terms of usefulness, the most useful for us is delta H. The net versus the gross. This is the gross. And so it's going to be quite a bit. And this is just a simple way to calculate the work done here by looking at the change in the moles of gas and calculating it that way. So what we're interested in here, this is the amount of heat, and this is going to always be the same for this particular reaction as written. This is per mole of reaction, but it's per moles of reaction as written. So 1 mole of reaction refers to the situation in which the extent of reaction is equal to 1 mole. This is not entirely correct here. And so if this is delta H, this is delta H per 2 moles of carbon monoxide. So it's not 1 mole, it's 2 moles of carbon monoxide per reacting with 1 mole of oxygen. And so there, in this case, it would be per 1 mole of oxygen per 2 moles of CO2. So let's say we form 4 moles of CO2, then we just double that, energy being extensive. And so it's not exactly, the wording on this is, I would reword it a little bit. It's per mole. Instead, I would just word this as per moles, maybe, of reaction as written. And so when I look at this is not kilojoules per mole for everything. When I look at this would be this many kilojoules per 1 mole of, this is sucrose, and so per mole of sucrose. That's correct. However, 1 mole of sucrose requires 12 moles of O2, so this would be per mole of sucrose. That's fine. But if I want to do this in terms of O2, I would write it like this. I'd write it minus 5.65 times 10 to the third kilojoules per 12 moles of O2. Or here, this would be minus 5.65 times 10 to the third kilojoules per 12 moles of CO2. And then finally, over here, it would be minus 5.65 times 10 to the third kilojoules per 11 moles of H2O. And so it's the number of moles as written, not necessarily one mole. It's to the number of moles as written in the equation. Well, this is very useful because this is now it's a fixed quantity. It's a fixed quantity, but we have some constraints. One, we have to do this under constant pressure. If we don't do this under constant pressure, we could get a different amount of heat. Two, there's only PV work. If you start using some of this chemical potential energy and convert it into let's say, this is exothermic, into other forms of work, you can. And so let's take a look at what I mean by that. And so this is the net. And so we have our delta H. Our delta H is minus 566 kilojoules. Let's keep it simple here. And that's this drop here. This is our delta H. And so this is QP. Or QP. Now, what we could do is we could do additional work. And so rather than converting it all into this heat, and so what I say is this is your usable income. If we wanted to do additional work, we could, and that's going to drop down Q, how much heat we end up generating. And so we could, usable income means we could just keep it as heat, or we could, now it's not converting the work, let's see, it's not converting the heat into work. What it is converting the chemical potential into work. Okay, so in this case, what did we see? In this case, who does the work? So what we have is we have 3 moles of gas. 3 moles of gas is around roughly 75 liters. And over here we have 2 moles of gas. 2 moles of gas is roughly 50 liters. And so the volume's contracting here. And so that allows us to determine who does the work. In this case, who's going to do the work will be there's something wrong with this. Surroundings does the work in that one, but there's something wrong with this because sucrose is not a gas. So I think that's a typo. Sucrose is usually a solid gas. In this case, we have 12 moles of gas going to 12 moles of gas and 1 mole of sucrose, and then we have, this is gas too. We have to be careful because maybe this is all gas. Sorry. If this is all gas, the state will change how much energy we have. And so if we have solid sucrose and we want to vaporize it, we've got to heat it up and vaporize it. And so this is very unusual because it's very hard to heat sugar up to vaporize it because sugar has a very low decomposition temperature. And usually when you heat it up, it starts to burn rather than vaporize. So I should have looked up this equation earlier, but maybe we'll come back to it. All right, so this is their usable income from the gross. We can keep it as heat or convert more of the original potential energy into work. So we restricted ourselves only to the P delta V work, but if we decide to do more work, then we could convert the delta H into that if we wanted to. And so let me give you a different scenario, one in which we don't do that. Let's say we had 1,000 kilojoules released to the surroundings here and so this is our gross energy that's released. And then let's say out of that, we have some work at constant pressure. And let's say we had to do this much work, constant pressure. Then the amount of heat after I'm subtracting out that work will be this. So this will be QP here. And if we do this under the restrictions, then QP is the same thing as delta H. And so some of the internal energy was converted, internal energy change, that is, some of the chemical potential energy was converted to work. But of course, we could convert more into work and get less heat. But delta H is the max we're going to get, because this is, you have no choice. This is your tax. And so this one you have no choice. But what you do with the remaining energy, internal energy change here, is up to you. And so delta H, this is our usable energy. So, for example, what we could do with that usable energy here is we could leave it as heat, or, maybe we just do more work, try to do more work with this. The more work we do, the less heat we're going to get. And so, and that's not converting heat into heat. Converting heat into heat is not what we're doing here. We're converting internal energy, that is this chemical potential energy, into work. So I guess the physical significance of the enthalpy change, delta H represents the heat transferred under constant pressure conditions. Yes, if we leave it as heat completely, but as I said before, we can try to get more work out of this because this is our net. And so what you do, let's say you had $100 of tax, you end up with $900. What you do with the $900, you could figure out. That's your buying potential energy. And so, in the same context here, what you do with those 900 kilojoules, you can try. Of course, we can try to convert it all into work, but due to inefficiencies, it's not. Thermodynamic inefficiencies, it's not possible to convert it entirely into work, but we can try to convert as much of this into work as possible. And so we can try to convert as much of that energy or leave it as heat as possible. All right, and so this is going to turn out to be extremely useful in that sense. But before we leave this, let's take a look at some scenarios here. Actually, we'll take a look at some scenarios from the homework. I'll do another video on that. And so there are some, we do this under constant pressure. So we go from liquid to gas. And so if that's the case, the system does work. And so the amount of energy we input here is going to depend on how much work we have to do for this particular change. And that's going to dictate how much heat we have to enter. And so this is kind of interesting because we would have an internal energy change like this. And so this would be our delta U here, or delta U, which would be QV in this particular case. Is fixed, If I did this in a bomb, I wouldn't be able to do any work. But in this case, the system has to do work. If the system has to do work, the system loses energy in doing the work. So this would be the work here. And then the amount of heat you have to input into this is this. This would be your QP here. And so there's this tax here, and so this is endothermic, so the amount of heat we have to input is going to be this, which is actually greater than the total energy change here. And this is our delta H here. And so in this case, delta H is larger in magnitude than delta U. And so, in other words, delta H is greater than delta U. We would have to input more energy. Now, delta H, we usually think in terms of magnitude, because it could be negative as well. I mean, and we'll look at a scenario there. Molar enthalpy of fusion, so this is 6.01. The difference in volume between the solid and the liquid is not huge, and so it's going to be a negligible amount of work, perhaps, when we compare it to this number here. And so some people only look at gases. Our book, for example, only looks at gases. So here we had 0 moles of gas, here we have 1 mole of gas. And they ignore everything else. So even though we know solid water, ice, is less dense than liquid water, so the volume does contract a little bit, they say it's so negligible, we'll ignore it. But we could calculate it if we want. It wouldn't be too difficult to calculate how much work is done. All right, so this is fixed now, and so these are going to be extremely useful to know. And so when we're interested in energy associated with reactions or processes, we want the delta H. And so for us, delta H is going to be the amount of energy involved. Energy in terms of enthalpy involved in these particular reactions. And in other words, what enthalpy is this. I know what delta H is. Delta H is equal to delta U plus or minus the work. Actually, let me do that first. I'll add that step in. Minus the work, minus P delta. Actually, let me fix this here. But the work is minus P delta B, so this ends up being delta U minus a minus P delta B, like that. And so that ends up being delta U plus P delta B. And so the initial, which one is what are we looking at here? We're going to call this the final and this the initial. So the final is going to equal U final plus P V final. And the initial here is going to equal U initial plus P V initial. And so what enthalpy is the total energy along with its pressure volume state. This is internal energy, and we've got to look at how this internal energy and the external surroundings interact. And the internal energy is going to interact with external surroundings by volume changes here. And so we need to define this additional energy term, which is PV here, to define how the energy is going to be exchanged with the surroundings and doing work. And so we just don't look at the internal energy. In a bomb, that's all we look at is the internal energy, because we don't care what the surroundings are not going to do work, and the bomb is not going to have work done on it by the surroundings. Okay. And so what we're after, and we don't measure this, we don't measure this way. This is going to be equal H final minus H initial. These are not determined. Typically. And the reason they're not determined typically is because of the U. The U term has a potential energy in there, and the potential energy term is difficult to calculate, absolutely. So we want delta H's. So the delta H's that we're going to have this is delta H of vaporization, so we call it delta H of vape. This is delta H of fusion, so we call it delta H of fusion. We also want delta H of reaction, RxN or R. So we want to know the energy associated with these changes here. So the thing we want to do is we want to figure out all the ways to determine delta H. And so let's take a look at standard states, standard thermodynamic states, we should call it, and standard enthalpy changes. So standard thermodynamic conditions equals this. Gases at 1 bar or 1 atmosphere, depending on the table you're looking at, and concentrations at 1 molar. There's no standard temperature. Oh, of course, the most common temperature is room temperature. And so we have something called the standard enthalpy of reaction. So all this means is 1 bar, 1 molar. The enthalpy change of a reaction in which all reactants and products are in their standard state. So this is called standard enthalpy change. Now, the standard state is the pure element or compound at a pressure of 1 bar at the temperature of interest. So there is no standard temperature. The temperature of interest most of the time is 298. And then if we have a mixture like a solution, we'll have the molarity be equal to 1 molar. So we have enthalpy diagrams like this, delta H. And remember, this is just the total energy with the PV state, so we can just see how the surroundings and the system interact by volume work changes. But we have endothermic and exothermic reactions. So this is the usable energy, so this is more useful than delta U. Delta U, we don't know. Is it going to be taxed? Is there going to be a bonus? But delta H already is compensated for the tax. So this is like, the after-tax cost of things. And so you always have to worry about how much the tax is going to cost. And so what we want to do is we want to learn all the ways to determine delta H. Delta H is going to be the most useful, again, for us. So what are all the ways to determine delta H? And so let's take a look at determining delta H. Probably one of the hardest ways is by calorimetry. This if we do calorimetry, we have 2 types. We have constant pressure. If we do constant pressure does not measure QP, it measures QV. From QV, we could get delta U. From delta U, we have to get delta H. In order to get delta H, we need to calculate the work that would have been done had they done it at constant pressure. We need to calculate work that would have been done under constant pressure. And so we have to do a little calculation. This is why knowing the molar volumes is very useful, because then we can do work calculations much faster. So that's constant pressure or bomb calorimetry. Then we have constant volume or coffee cup calorimetry. Coffee cup calorimetry is going to be a lot easier because in coffee cup calorimetry, we measure QP. If it expands, it expands. If it contracts, it contracts. Or if nothing happens, nothing happens. For ours, pretty much nothing happened. There's no tax, there's no bonus. So we had a zero tax environment. And so when you have a zero tax environment, then delta U and delta H are the same. And so we'll have different scenarios. So for example, let's go back up here. Delta U, let's say absolute value, is greater than delta H if there's a tax. It could be exo or endo. That's why I put the absolute values there. Delta U is equal to delta H if there's no tax. This is just gross income versus net income. Delta U is greater than, oops, did I do that? I did that wrong, didn't I? Is greater than delta H, absolute value. Sorry, I did this wrong. This is not a tax. I should say bonus here, because you're getting more delta H. Your net is more income than your gross. Here, your net income is less than your gross income. That's a tax. Sorry about that. So that would be the tax. So sometimes delta U and delta H are the same. So when we did our calorimetry, it didn't matter if we did it in a bomb or coffee cup. We're going to get the same amount of heat because there was no tax bonus. The volume pretty much stayed constant. 50 plus 50, yields 100. But if there is a tax or bonus, then we're going to get a different amount of heat. And so under constant, what am I doing? Constant pressure. Oops, I made another mistake here. Bomb calorimetry is not constant pressure. Bomb calorimetry is constant volume. Coffee cup calorimetry is constant pressure. So I'm not sure what's going on with my brain today, but anyway, this is constant pressure, which is delta H, and so we would be done there. And so definitely bomb calorimetry, there's this extra step that's involved in converting delta U to delta H. We'll go through an example of that later. Okay, that's one way, but there are others. The other ways of determining are by Hess's law. Hess's law is, if we know some equations, so what we do is we sum up reactions that are with known delta H's to get net reaction that's desired. And so in other words, what we do is delta H of the reaction of interest is just equal to delta H, let's say reaction 1 plus delta H reaction 2 plus, and so we add the equations, we add the delta H's. So this is Hess's law. There's certain things with Hess's law. So delta H of reverse is equal to minus delta H of forward. And then if we do n times the reaction, let's say we double it, the number of moles, or triple the number of moles, then we'll have to do n times delta H for that reaction. Those are things. There's another variation of Hess's law, and this is Hess's law using standard formation reactions. This could be also for processes as well. It doesn't have to be a reaction. It could be a physical change. So the other method is using Hess's law with these standard formation reactions. And this is the easiest method. The easiest method is the delta H for the reaction or process we're interested in is equal to the sum of nu. Nu is the coefficient times the delta H standard, that's that little superscript, and F means formation of the products. And so we sum up the product standard formation enthalpies, multiplied by their coefficient, and subtract that the sum of nu, this is nu P, this is nu R, this is the coefficients of the delta H of the formation of the reactants. And so this is the products minus the reactants, and we sum it up. And so this is the easiest method for determining delta H. And so let's talk about what standard, oops, okay, I think maybe I jumped this slide. So this is Hess's law. Delta H is extensive. Well, delta H is kind of a ratio because the typical units of delta H are kilojoules per mole. And so the heat is extensive. You know, this is kind of intensive here. So we should say energy, or Q, is an extensive property. So enthalpy change is directly proportional to the amount of substance in a system. So I guess what they're saying here is that what we're going to do is we're going to convert this. So this is per mole as written. So 1, 1, 2. Here we're going to multiply everything by 1/2. So we have to multiply our delta H by 1/2. So I guess in that context it is extensive here. And so it depends on how you look at it. And so if we do this by 1/2, then this is not per mole. You know, these two per moles are different. You know, and so in this case, it's kilojoules per half mole of N2, kilojoules per half mole of O2, and kilojoules per mole of NO. Whereas this one here is per 2 moles of NO. This one here is per 1 mole of NO. And so in that context, it's an intensive property because, you know, if you have 2 moles, you double it, right? But the ratio is the same. Okay. In another context, it's extensive because, yeah, we're going to get twice as much energy. But, you know, since they're not changing the units here, this is incorrect. And so this should be plus 180.50 kilojoules per 2 moles of NO, whereas this is 90.25 kilojoules per 1 mole of NO. This is critical because in a formation reactions are always per 1 mole of the product. And so this is called a formation reaction, the second one here. The first one is 2 times the formation reaction, so it's double the formation reaction. Because a formation reaction always has to be per mole of product. So we are forming 1 mole of NO. Here we're forming 2 moles of NO. That's not a formation reaction. That's double the formation reaction. Okay, now if we reverse it, the sign changes. So if I take this formation reaction and go backwards here, then it's this. But now this is not a formation, it's formation of a single product. And so here we're forming N2 and O2, so this is not a formation reaction. And so let's define a formation reaction. They haven't defined it quite yet. Well, this is Hess's law. So Hess's law, we're just summing up the steps, you know. And so this is the first step here. 1/2 N2 plus O2 goes to NO plus 1/2 O2. This would be the second step here. NO plus 1/2 O2 goes to NO2, and we're here. But we could get here a different way. We could just go by this route, which is 1/2 N2 plus O2 goes to NO2. So different ways we can get there. This is Hess's law here. Where we sum up these 2 steps, we end up in the same place as the single step here. So this is Hess's law. Hess's law says the sum of the reactions, reaction 1 plus reaction 2 gets us to the same place there, which gives us the same amount of energy. And so here they're summing up reaction 1 plus reaction 2, and we get the same net reaction. And so these ones with known delta H's can be used to determine the unknown delta H. So the unknown delta H's, they just add these 2 together to get 33.18. Okay, now that's the harder method of Hess's law. The easier method of Hess's law is restrict only to formation reactions. And so what is a formation reaction? The standard enthalpy of formation, what do they say, is for the formation of 1 mole, this is 1 mole of substance from the elements in their standard states. And so from the elements in their standard states. And so that would be a formation reaction. So this would be a formation reaction for diamond. We're going to form 1 mole of diamond from the element in their standard state. The standard state of carbon is graphite. Diamond is not the standard state, and so graphite is. And so this is, we can call delta H a formation, and if we do this under standard conditions are 1 bar pressure, then that would be it. Here, this is a formation reaction too, because the standard state of bromine is a liquid, not a gas. Bromine is one of the elements that are liquid at room temperature and normal pressure, 1 bar pressure. 1 bar pressure is about 1 atmosphere. And so this is delta H of formation for bromine. So we'd say delta H of formation for bromine liquid is 30.91 kilojoules. We can compile these into tables like this. So we can pick, let's pick a couple of these and see what it comes out to. So let's pick ethanol. Ethanol, we see a delta H of formation under standard conditions. This is standard enthalpy of formation of minus 277.7. And so let's go ahead and write what the formation reaction for this looks like. So I'm going to insert that here. So we need to form 1 mole of ethanol. I'm going to write ethanol in my standard way like this. From the elements in their standard state. So ethanol is a liquid. And so this is going to be delta H of formation under standard conditions here. The standard form of carbon is graphite. So we'll have carbon in graphite form. And how many carbons do we need? We need 2 carbon graphites. The standard elemental form of hydrogen is H2, and I need 6 of those, so I'll need 3 H2 gas. And then I have oxygen. Well, I only have 1 oxygen here, but the standard form is O2, so I'll take 1/2 a mole of O2 gas. So this would be called the formation reaction. We rarely have to write these out because of the equation. Because of the equation, all these elements cancel out. Otherwise, it's improperly balanced. And so when we do our reaction, let's say, how would I use this? How I'd use this is maybe in the combustion of ethanol. So we have O2 goes to CO2 plus H2O liquid. And so how many CO2s? I need 2 CO2s. And that's 6, so I need 3 H2Os, and that gives me 4 plus 3 is 7. And so I need 6 oxygens plus 1 oxygen here, and that gives it to me here. And so I would rarely write this out because this is the standard enthalpy of formation for ethanol, CH3, CH2OH liquid. And so if I want to figure out the delta H for this reaction, then that's equal to the delta H of formation of the products. So I have 2 moles of CO2, and then I look up the delta H of formation of CO2 in the table. And then I have 3 moles of H2O, and then I'd look up the delta H standard enthalpy of formation of H2O liquid. Okay. So those are the products, and then I go minus the reactants. And so the reactants here are going to be 1 mole of ethanol times delta H formation of ethanol. And then I have 3 moles of O2. So this is plus 3 moles of O2 times delta H formation of O2. Delta H of formation of O2 is 0. That we know because the reason that it's 0 is because it's forming O2 from O2. So this is formation of 1 mole of O2 gas from the elements in their standard form. The elements in their standard form is O2 gas. So if we go from O2 gas to O2 gas, then delta H of formation for this should be equal to 0. And so the standard enthalpy of formation for any element in their standard elemental form is 0. pause this for a second. So we would just look up these values in a table. Let's see. This is not the table here. This is the table here. So we could get the values, and most of these are located in Appendix D. And there's a more comprehensive table. And so this beats doing bomb calorimetry. The other way we could have gotten delta H for this particular reaction is burn it in the bomb. We burn it in the bomb, and then we get QV. From QV, here, we could burn this in a bomb. We could get QV. And then from QV, we could get delta U. But let's see, is there work in this particular? And so we go from 3 moles of gas here to 2 moles of gas. This is 1 mole of liquid and 3 moles of liquid. So the volume doesn't change much with the liquids. It's the gas that primarily changes because we see huge volume changes with gas. And so what we'd have to do is we'd have to calculate how much work would have been done under constant pressure. And so that just means, well, it depends on how much ethanol we burned in there, and then we figure out how much the volume changed. We can calculate the work, and then we'll correct the amount of net, that is, delta H for that. And so, in other words, we can derive delta H from delta U. So that's quite a bit more work. This is a lot easier here. So we just look these up in the table here, and then there's no problem. This is just showing the 0 point. The 0 point here is formation of elements from the elements. In some cases, the compounds are more stable than the elements. In other cases, the compounds are less stable than the elements here. All right, there is one tricky thing here, because you see the delta H of formation are equal to 0 for elements in elemental form. So enthalpies of formation of elements, because you're forming an element from an element. So this would be like, okay, we need to form 1 mole of hydrogen gas. We're going to form it from hydrogen gas. And so elements in elemental form have a delta H of formation of 0. However, there are 2 tables in this. And so we'll look at that in a moment. And so here it's just showing enthalpy of formation. So if we want to form formaldehyde, we're going to need two hydrogens, 1 carbon, and 1 oxygen. And so we can just do the elements like this. That's the formation. And so let's see, is formaldehyde in the table? No, it's not in this table, but it's in the Appendix D table, I'm sure. And then what we're going to do is we're going to use these. And so this is just showing how Hess's law works for this. But all we do is we just use the equation. That is, we take the standard enthalpies of the product minus the standard enthalpies of the reactants, sum those up. And so this is the same thing. This is the equation we have to pay attention to. You don't need to know these enthalpy diagrams. We call this enthalpy diagram, but it's essentially showing you how we add these up to get the steps. But this is the key equation here, and so this equation is critical. This is the easiest way to determine delta H's here. Okay, there is one thing about the table, though. And one thing about the table are ions. The ions have a different 0 point. Zero. So what we have for the 0 point is this. We define the enthalpy of formation of H plus is defined as 0 kilojoules per mole. And so what that means is that if we want to form H plus, this is going to be 1 molar H plus, because it's under standard conditions. We're going to form that from the elements in the elemental form, so we'll have to take half a hydrogen gas. And this is not really 0, because in order to form H plus, we have to break the bond. So we have a mole of hydrogen, half a mole of hydrogen. We've got to break a half a mole of bonds. And then we have to ionize it. And then we have to dissolve it in water. And so that process is not going to result into zero energy, but it's just defined as zero energy. And how can this work? Well, that's going to lead to an error. It's going to lead to an error, but what happens is you cannot form a cation without forming an anion. And so the way we do this is we put all the enthalpy into the anion. And so I'm not going to use this one with water here. I'm going to use another example here with hydrochloric acid. So let's say we want the delta H formation of HCl. And we could figure this out. I think it comes out to minus 167 kilojoules. And so how much of this is due to the formation of H plus, and how much of this is due to the formation of chloride? And so that's something we could try to calculate, but it's quite difficult. And so if we have two unknowns, we need two equations. So with two unknowns, let's say x and y, normally we do a system of equations, but in this case, we are not going to do a system of equations because there's no other equation that we're going to come up with that's going to be easy. So instead of doing a system of equations, we're going to do this. We're going to assume that one of these is zero. So x, we're just going to assume x is zero. If x is zero, then that means y is equal to minus 167 kilojoules. And then you go, that's wrong. This is wrong, but it works because, but it works. And the way it works is this. All the cations are going to be in error in one direction. So all the cations are going to be in error, let's say in this direction here. But all the anions are going to be in error in the opposite direction. And so this is the error due to the cation assumption. This is the error due to the anion assumption. When you add up the errors due to the cation, they cancel each other out. And so the situation is you can't form a cation without an anion. And so the errors will always cancel one another out. And so this works because I need both cation and anion. And so errors cancel to form both. And so when we take x plus y, we get the correct answer, minus 167 kilojoules. And so when we look at the table here, we'll see that H plus is just arbitrarily defined as zero. That's by definition. It's not true. And that means all the cations are going to be in error in one direction, and all the anions are going to be in error in the opposite direction. And then we add them together, and the errors cancel. And so that's one thing you have to keep in mind when using this particular table. And then we look at applications. For example, fuels. You want to know the energy. So the fuels. And so we'll look at these applications later, and we'll look at some sample calculations later. So I'll post another video. All right, thanks for watching.